All right, if there are no questions, we're going to continue with gas mixtures. No? We have two ways, actually, more than two ways, but when we think about a gas mixture, let's say air. Did we look at air last time, or looking at it different? We did air last time. There are going to be three ways we visualize this mixture. The first way is this. Air is 80% nitrogen, 20% oxygen. What kind of percentage is that? Is that a mass percentage or a mole percentage? It's a mole percentage. A mole percentage means if I had 100 molecules of air in here, then 80 of them would be nitrogen, and 20 of them would be oxygen. This is an 80 to 20 ratio of nitrogen to oxygen. And this is what we call a mole percent. What's another way of visualizing this? Well, similar to a mole percent is something called a mole fraction. Mole fraction shouldn't be too hard. 20 out of 100. 20 out of 100 would be nitrogen, right? And so the mole fraction for nitrogen would be 20 out of 100, which is the number of moles of A, in this case nitrogen, over the total number of moles. A mole fraction of nitrogen sometimes is given the symbol chi. So this is the chi N2 here, where A is N2. 80 out of 100 would be the mole fraction for oxygen, called component B, or N total. This is chi O2. And so this is a mole fraction. This is the moles. And the total moles, N total, is equal to the sum of the mole fractions, or not mole fractions, the sum of the moles of each component I. And so it just equals the moles of A plus the moles of B plus however many components we have. So moles of nitrogen plus moles of oxygen. Total moles. Uh-huh.
Isn't there a 100?
Oops.
Isn't that oxygen?
Yeah, you're right. Sorry. This is oxygen. 20, and this should be nitrogen. 80 out of 100. Thanks for catching that. All right, so, basically a percentage, the percentage is just the mole fraction, N, what do I call this? NA over N total times 100. And so we can always convert a mole fraction into a percentage by just multiplying by 100%. As a mole fraction, it's the same thing. If you have 50%, the fraction is 1/2, right? It's not difficult. But there are other ways of visualizing this as well. One way of visualizing this mixture is as a Dalton's mixture. If we try to visualize this as a Dalton's, what was Dalton's law? Think about Dalton's law. Dalton's law says that the total pressure is equal to the sum of the partial pressures. And so when we do this, trying to look at this in terms of Dalton's, let's put some numbers on here. Let's keep the numbers simple. Let's say I have 100 liters of gas, of air. And this is going to be at 1.0 atmospheres of pressure. And let's keep the temperature at 25.0 degrees C, room temperature. Okay, so I have 100 liters of mixture. Now Dalton says, well, how much of that mixture is nitrogen? Well, you know, using mole fractions, we can say 20% or 80%. Actually, 80% of the molecules are nitrogen, 20% are oxygen. But as far as Dalton's goes, how much nitrogen do I have here? How many, let's say, how many liters of nitrogen do I have? Yes, I'd have 100 liters of nitrogen. 100 liters of nitrogen. All right, and also in this mixture, how many liters of oxygen would I have? I'd have 100 liters of oxygen here. Did I already do this? 100 liters of oxygen. And so what I'm going to do is I'm going to take, 80% of the molecules and then just put those in this box here. And then the O2, oops, actually, I'm sorry. Blue should be used for nitrogen. So I got the nitrogen over here, and then I'm going to have 100 liters of O2. Now, what's going to happen with the pressure? The pressure is going to be caused by the collisions. Over here in the mixture, we got collisions of the blue and collisions of the red. And the combined collisions gives us a total pressure of 1 atmosphere. But over here, do I have any red? No, so all I'm looking at are the collisions of the blue. And actually, they're going to be 20% fewer molecules. If there are 20% fewer molecules, they're going to be 20% fewer collisions, which means that the pressure is going to go down. And so what is the pressure here? Pressure is 0.8 atmospheres. Now, if I get rid of all the nitrogens and just look at the oxygens, then I'm going to have these collisions here. 80% of the collisions are going to be gone, so the remaining are going to generate 0.2 atmospheres. And so this is Dalton's law. Dalton's law says the partial pressure of nitrogen plus the partial pressure of oxygen, there's only two components here, should equal the total pressure. And so 0.8 atmospheres plus 0.2 atmospheres is going to equal 1 atmosphere. And then this is going to equal P total, the total pressure. And so normally when people think about Dalton's law, P total is equal to the sum of the partial pressures over however many gases you have. But what's going on with the volume? So if I take 100 liters of nitrogen plus 100 liters of oxygen, how many liters of mixture should I get? And so 100 liters of nitrogen plus 100 liters of oxygen should yield 100 liters total. And so in terms of Dalton's law, P total is the sum of the partial pressures. So partial pressure gas A, partial pressure gas B, ... however many gases we have. And so this would be nitrogen and oxygen. But here, the volume, in terms of Dalton's, is constant. And so V total is equal to the volume of nitrogen, which is equal to the volume of oxygen. In other words, V total is equal to VA, which is equal to VB, which is equal to VC, etc. In other words, the volume is constant. And so when somebody asks you, what is the volume of any gas in this mixture, then the volume is easy because it's the same as the total volume. Check something here.